Welcome back, literature fans. Today we're starting another series of videos on algebraic calculus. I call it quadrature of the curves y equals x to the n. And we've done this before, and I want to regurgitate, do it again. It's always good. So here we go. We're based on Professor Wildberger's famous Math Problem 10b video, which is also article, a new proof of Cavalieri's formula in the American Monthly magazine, and we're also basing it on his polynumbers. So this is all Wildberger stuff. You might ask, what's polynumbers? Well, that's polynumbers. Believe it or not, we're going to reach this level, and it looks daunting at first, but we'll get there. Don't worry about it. Anyways, we are the algebraic calculus is based on the invariant properties of area and slope, additivity, linearity, normalization, dilation, translation. This is all Wildberger stuff, but it's great stuff. So, you know, what specifically we're going to look at dilation on one side and translation on this other side. It's leveraging dilation against translation. For example, here's a curve y equals x squared. And so you can see, it's pretty busy, but translation is simply, we're translating by alpha. So x equals t plus alpha. You got the x-axis, and superimposed is the t-axis. X goes from 0 alpha to alpha, t goes from minus alpha, 0, and then alpha. Pretty simple. So when you do the squared, so it's t plus alpha squared, and this is a binomial expansion, t squared plus 2 alpha t plus alpha squared. So you get these three functions, constant, linear, and another quadratic, and that's this curve right here from 0 to 2 alpha on the x-axis. Well, excuse me, from alpha to 2 alpha on the x-axis gives you this on the t-axis. So we're after this wedge from alpha to 2 alpha on the x-axis. That's this wedge here, the area. And that equals the area of these three functions, the constant, linear, and quadratic from the t perspective. So we're leveraging one against the other. And similarly, slope, you know, we're after this slope at x equals 2 alpha. Well, that's the same as the slope at t equals alpha, and you can see that the constant gives you 0. The linear, that gives you some slope, and the quadratic, that gives you another slope. So again, we're leveraging these things, and that's our approach. What we are doing is we're using kind of an operational approach. The term operational shouldn't be a strange thing. It's wired into the algebraic calculus from the beginning. It's an operational. We're headed toward operational calculus, and so that's box operators. And what is that? Well, the box of x to the n is simply x to the n times x, rise times run. That's a box. And the diagonal, the characteristic diagonal, is x to the n divided by x. Notice you increase the power by 1, and here you decrease the power by 1. So they're inverse type relationships. We're not using the limit, at least we're ignorant. We're limit ignoramus, okay? Especially with epsilon delta. None of that. We're not using that. At least we're not aware of that, so forget that. That's not our approach. Not in the algebraic calculus. That's a difference between regular calculus. Regular calculus, it's all about the limit. And you can go nowhere without the limit. Here, we're ignorant of the limit. Okay, fine. We're also using what I call a simultaneous approach to this algebraic calculus. Namely, we're doing the integral and the derivative together in one video like this. Okay? We're not doing, this and then doing it for a number of months and then come back to this. And no, none of that. We're doing it simultaneously together. And there's no preference, the integral or the derivative, which one we do first. No, it's simultaneous. And integral stands on its own and the derivative stands on its own. We can do them. And so that's the approach. And the other approach that we're using is we're starting simple and we're becoming more complex. Namely, we're starting with basic multiplication and division. And, you look at this. I say that's pretty simple. You have some object, beta, divided by alpha. And then you multiply it by alpha, you get back beta. That's pretty simple, right? And of course, beta times alpha and then divided by alpha. Again, that's beta. These are inverse operations. That's just the multiplicative inverse of, multiplication and division are inverse operations. But before we think it's way too simple, consider this. What if beta is some complicated object like 2x third plus minus 5x minus x plus 3, and we're dividing by alpha, which is equal to x plus 3. So this is long division. And notice that if we try to do this, we encounter what looks like a limiting process because, the end result is 2x squared minus 11x plus 32 minus 93x to the minus 1 plus 279 x to the minus 2 ... This just goes on forever, and it just goes on forever. You can do this with synthetic division too, and you get the same thing, long division and synthetic division. Anyways, I just want to let you know that, interesting, there is such a thing as a limiting process. If you insist on doing this and finishing this, a lot of times you will encounter in division a ongoing process that goes on forever. For example, if you try to divide by 7 exactly, well, you can't do it. You got a repeating decimal that just goes on forever. And so division is a little tricky. But notice also how the algebra, how powerful it is, that despite its complexity, well, alpha cancels alpha and you get back beta exactly. And that needs to be appreciated. So the algebraic approach is powerful. Even from the get-go, we can see simple multiplication and division, powerful stuff. So the next step up for multiplication and division is these box and diag operators, right? So the definition of the box of x to the n is simply x to the n times x. That's rise times run. And diag of x to the n, that's a characteristic diagonal, is rise divided by run. X to the n divided by x. Well, simply put, it increases the power by 1 on the box, and diag decreases by 1. So again, these are inverse operations. So the box of the diag of x to the n is x to the n. And the diag of the box of x to the n is x to the n. So we get back same thing. So you see this progression, how we're starting simple multiplication, division, and now we introduce these box operators. And the next thing, we go to the integral and the derivative. And the integral is x to the n plus 1 over n plus 1. And the derivative is n times x to the n minus 1. The challenge becomes of proving these factors. K sub n is 1 over n plus 1. That's this factor over here, 1 over n plus 1. And C sub n, that's the slope factor, is n. That becomes the challenge in this whole algebraic calculus, is how to find these for any n. Now we know what the k0 and k1, this would be constant and the linear. For constant, that's just a rectangle. K0 is 1 and k1 is 1/2. That's a triangle. Similarly for the slope factor is a C0. Well, we know that's constant, that's a 0 slope always, and C1 that's 1 times. So these we know. Anyway, so this is our approach, and we will continue. So thank you.